How to find and prevent deadlocks in code. Have you ever found your program frozen, with threads waiting endlessly for each other? This frustrating situation is known as a deadlock. Understanding how to identify and prevent deadlocks is essential for anyone working with concurrent programming. Let's break down how you can tackle this issue effectively. First, let's talk about how to find deadlocks. The symptoms are often clear. You might notice threads or processes that seem to be stuck, waiting indefinitely. Keeping an eye on thread states, resource usage, and system logs can help you spot these issues early. Next, consider using debugging tools available in many development environments. These tools analyze thread dumps or stack traces, revealing which threads hold locks and which are waiting. This can give you a clear picture of where the deadlock is occurring. Another effective method is code review. Look for areas where multiple locks are acquired, especially if different threads take locks in varying orders. This is a common cause of deadlocks and can be identified through careful examination of your code. Incorporating logging and tracing is also beneficial. By adding detailed logging around lock acquisition and releases, you can trace the sequence of events that lead to a deadlock. This information is invaluable for understanding the flow of your application. Now let's shift gears to preventing deadlocks. Deadlocks occur under for necessary conditions: mutual exclusion, hold and wait, no preemption, and circular wait. To prevent deadlocks, you need to break at least one of these conditions. One effective strategy is lock ordering. By defining a global order for acquiring locks, such as always locking resource A before resource B, you can prevent circular wait situations. Ensure that all threads follow this order to avoid deadlocks. Another approach is implementing lock timeout and backoff strategies. Set time limits for how long a thread can wait to acquire a lock. If it cannot obtain all required locks within this time frame, it should release any held locks, wait briefly, and then retry. This method helps reduce the chances of deadlock. You can also avoid hold and wait situations by requiring threads to request all needed resources at once. If not all resources are available, the thread should release any held resources and try again later. This prevents threads from holding resources while waiting for others. Setting resource allocation limits is another practical solution. Use mathematical conditions to ensure your system has enough resources to avoid deadlock. For instance, if you have P processes each needing N resources, ensure that the total resources R meet the condition R is greater than or equal to P times N minus 1 plus 1. This guarantees at least one process can proceed without waiting indefinitely. Lastly, consider using higher-level concurrency constructs. Opt for concurrent data structures and synchronization utilities that manage locking internally and help avoid deadlocks. Examples include semaphores, monitors, or transactional memory. In practical applications, always document and enforce a consistent lock acquisition order when designing multi-threaded code. Utilize lock timeout and retry mechanisms, especially in complex systems. During testing, use debugging tools to analyze thread dumps and catch potential deadlocks early. Stress test your concurrency scenarios thoroughly to expose any deadlocks before your software goes live. By applying these strategies, you can effectively find and prevent deadlocks, ensuring your software operates smoothly in concurrent environments.